Our last video looked at vertical asymptotes of rational functions. This video will discuss other kinds of asymptotes. So if a rational function is of the form ax plus bx over qx, and here a, b, and q are all polynomials with the degree of b of x being less than the degree of q of x. This is the form of the rational function that you'll find if you do long division. So if a rational function is this, then the graph is close to the graph of a of x, this first polynomial, for big and small values of x. This sentence probably doesn't make a lot of sense until we do some examples. So let's start with a simple example. How about the function 2 plus 1 over x? So this is the correct form because I'm saying a of x is equal to 2, b of x is equal to 1, and q of x is equal to x. This function has behavior for large and small values of x that's close to 2. So in the picture, what that means is that I could draw a guideline at 2. So here's the line at 2. If I plug in a very small value for x, so if I'm very on the left of this picture, if I'm way over here on the left, the graph is close to 2. And if I'm on the right, the same thing happens. This graph has a division by 0 at x equals 0. That means I get a vertical asymptote. So the graph is going to look like the following. If I stick in a very big negative number, I'm close to 2. As I get closer to the vertical asymptote, the graph goes down. I think the picture is going to look something like this. And then similarly, on the right side of the picture, if I get a very big positive number, the graph is close to 2. Otherwise, the graph is affected by the behavior of this vertical asymptote. So here is this side of the picture. The reason why this works is because if you stick in a very big number for x, then 1 over x is insignificant. It's like 1 over 1,000,000 or 1 over 1,000,000,000. This number isn't very big at all for large values of x. So the behavior of the graph is greatly influenced by this a of x function, or the 2. Let's see a few more examples. What about the graph of 1 minus x minus 1 over x minus 1? Let's draw this picture over here. Here, my a of x function is the line 1 minus x. So to draw the graph of this function, I'm going to draw the graph of the line 1 minus x as a guide for what's going on. So here is the diagonal line 1 minus x. I also see I have a vertical asymptote at x equals 1. So at x equals 1 here, I also get a vertical asymptote. So I'm going to use these as guidelines for what's happening with my rational function. I can plug in a very negative number, and the behavior of this function is going to be close to that of the line. I could determine that the function is slightly above the line by plugging in values for x that are negative, or I could say plug in x equals 0. If I plug in x equals 0, I get 2, meaning that the graph is in this region here, behaving similar to what I'm drawing in red. Similarly, you can plot a couple points to determine which side of this diagonal line we're actually on, but I think if you do, you'll get a picture that looks something like this. So the behavior is dictated by the vertical asymptote near 1, and as I get larger and larger to the right, the behavior approaches that of the diagonal line. So this is called a slant asymptote because it's a slanted line. Let's do a couple more examples. How about the graph of x squared minus x over x minus 1 squared? Okay, my a of x function is x squared. That means for large and small values, my function is going to behave like a parabola. I have a vertical asymptote at 1 again. And I notice that if I plug in x equals 0, I get 0. So putting all these observations together, let's see what happens. So I'm going to begin as a guide by sketching the graph of this parabola x squared. So here's my parabola x squared. Then I will notice I have a vertical asymptote at 1, so I'm going to also draw a guideline here. I am crossing the graph, the y-axis here at 0, because I notice if I plug in x equals 0, I get 0 minus 0. So now I think I'm ready to sketch the graph. Again, I could plot more points to see exactly what's happening, but in this picture, I'm going to hug the parabola for negative values and positive values like this. So it's going to come in, it's going to cross the axis here at 0 and then get closer to my vertical asymptote. And similarly, I could plot a few points on the right if I'm ever confused of what's happening, and I'd find behavior that's similar to this. So there's a graph of this rational function. Let's finish the video with one final example. The next video I'll even give more opportunities to graph rational functions, and in the next follow-up video I'm even going to give a how-to guide on how to graph these rational functions. But for this video, let's do the example x squared plus 2x plus 3 over x plus 1. Now I wanted to finish with this example so that you could realize that I first sometimes need to write my rational function in this form. It's not currently of the correct form because this top function has degree 2, where the bottom function has degree 1. So the first step is to do long division. I did that in preparation of this video, so I'm not going to show you the steps. If you need to get a refresher on the long division, go back to that video. But I think if you do the long division, you'll find x plus 1 plus 2 over x plus 1. Now I'm ready to use the logic I'm introducing in this video. I can start by sketching the graph of the function x plus 1. That is a diagonal line that goes like this. So there's the guideline, x equals 1, x plus 1. I have a vertical asymptote at negative 1, so I have vertical asymptote here. Those are my guidelines. I can plug in certain values. So for example, if I plug in x equals 1, I get a positive number, meaning I'm up here on the graph. I can plug in a number a little bit less than negative 1. That would help me determine the overall location, but I think in this picture, I'd get something that looks like this. Okay, wonderful.